Okay, so let's do some cleanup first. So I posted a bulleted list after class for those who were not able to stay, in sync, so that they can go and finish that part. There's not really too much. The video apparently is going to be available, so you can always go back and look at the video. So the tip of the iceberg is what we did in Ubuntu, because Ubuntu is, you can't learn Ubuntu in an hour, or maybe even in a day or week or month. So the main thing is that the biggest exercise was we created like a 3-level directory structure. From the home directory we created level 1 and then a level 2, and then we created a file and placed it in level 2 and then copied it to level 1, and then we tried to delete it. You would have found that if you don't use that special -R flag, so Ubuntu has these command modifiers, those -R and all of those things. They are available for just about every command. So different variations of the command. If you don't use those flags, you'll get the default choice. So how do you remember this? You don't. You just Google it, because there's no point in trying to memorize those things. So essentially, you can't delete a directory which is not empty, and therefore you have to use the -R option. But then of course you lose everything. Now, there's one thing I wanted to mention, and that has to do with the document I was using, the cheat sheet as I called it. Let me first recover it. So every command that you would need in this class, well actually I don't know any commands outside of this, and I've been using Ubuntu for 12 years. I look up anything else that you need, but this is basically what you need. Yeah. Let me just plug the holes in the sense that I may have missed certain things. So you see here, ls-l, list files in long format. That means it's going to tell you the date of creation and so many other things. So there are other modifiers. There are hidden files in the directories. If you put ls-a, it will list the hidden files also. Now typically you don't want to do that, because their reasoning is, if you can see a hidden file, then you're more likely to destroy it. Those hidden files are needed by the system. And so that's why they keep it hidden unless you specifically ask for them to be shown. And then if you put L and A, it combines these two aspects together. Alright, the sudo. So you'll have occasion to use this sudo when we get into ROS. So certain things require permission. It requires user permission. So sudo literally is derived from super user do. I mean, they just make it up. The early Linux people, they were having fun. Some of the commands will appear really strange, but they started many years ago, and these commands are not going to be changed because they are there. It's historic. So sudo, often, suppose you try to delete something, it'll say you don't have permissions. So it's saying, do you really want to do this? In other words, it's acting as a check on you. So when you say sudo and then complete the command, it's not just for deletion, it's for all kinds of other things. When something doesn't work, read the message it's telling you and then try putting a sudo in front. Then it'll ask you to enter your password. So that's confirmation that you are not drunk and you're really trying to do something that you're asking you to do. Now, were you able to run ROS code? So why don't you go to your home directory? If it doesn't run, don't worry. We'll make it run during the course of this afternoon. But go to your home directory. You know how to do that, right? Because normally you land in your home directory after booting up. And then you type the command ROS code. That's the command. Now, typically in a tutorial, they'll show you a dollar here to indicate that you're entering it in a Unix terminal. They won't put the full path because they think you know which directory is meant. So the dollar indicates that it's a terminal command. And then you hit return. The question is, Does it run cleanly? The question for you. There should be no red. So read, like Unix will dump a lot of stuff on a screen. Most of the time you can ignore it. But if something red shows up, it means that there is a problem. You can't go past it without resolving the problem. So, is everybody able to run ROS code? Anybody was able to run it? Nobody. So when I run it, I'll show you. So what should be there? So by the way, I talked to you about sudo, right? There's something known as the .bash rc file. So in your home directory, I want you to run ls -a and tell me whether you see a .bash rc file show up. Is it there? Okay. So what that file is, it's a set of, anytime you open a terminal, it runs that file, the .bash rc file. It is literally creating the environment for you. And that environment is filled with many instructions that you don't care about, but they have to be run in Linux. And right at the bottom, there are some instructions that are very particular to what you're doing. For instance, we are working with ROS Noetic. So that has to have a corresponding command in the .bash rc file. I'll show it to you. And only then your environment is set up. So the fact that it's not recognizing ROS core could mean that the bash rc file does not have that command. Why don't we go and look at it right now? So, but there's something else I wanted to do before shutting down this document. And that is this one. So try doing this, gedit home/.bashrc. I want to know whether the editor gedit is available to you. So it's the most common Linux editor that I use. Other people use Nano. I don't like Nano. gedit uses more memory. I prefer that because it has more features. It makes it look like a normal editor. So gedit home/ and the name of the file is .bashrc. So a good thing that gedit is already loaded. Sometimes Unix comes in stripped down fashion because they're saying, hey, you load whatever you want. I'm not going to dump everything into this package because it gets bigger and bigger. So it's a good thing that the gedit is available. So don't edit anything, don't touch anything, just close the file. You don't even have to save it, just close it. And we'll follow up on that. Okay, the other thing is, I told you about tab completion. And I also told you that sometimes results, moving files, renaming files can be achieved through the desktop GUI icons, just like you do in Windows and Mac. Now, this one here, the grep and pipes command, it's a short form for something extremely powerful. So I'm not going to teach you about it, but this grep and pipes in combination, it's a very powerful command line instruction in Unix. So if you want to jump ahead, you can Google it tonight and see what you find out about it, because there'll be lots of sample, on the internet as to what it does. Very powerful feature. So this is a very brief operating system because, even though you're not going to be a ROS expert, it's always important to know the environment in which you're operating. So this is the architecture. We talked briefly about it this morning. We're using Ubuntu 20.04. And I'm using MATLAB 2023A. You may be off, maybe you're using 2023B. It doesn't matter. MATLAB releases 2 versions every year. I typically don't do the Bs. I go from A to the next year's A. So the next year's A is very new. I wait till the end of the semester because typically you don't want programs that are not running anymore. So it's good to always do the upgrade between important periods in your academic life. Otherwise, code might not run. We're using ROS Noetic. So ROS Noetic also comes in versions. So ROS Noetic is the last ROS 1 version. From now on, it's going to be ROS 2. And my understanding is that ROS 2 is all the commands are slightly different, and it's a big learning curve. I don't know ROS 2. My task, one of my tasks this summer is to switch to ROS 2. So the other group had a very good discussion on ROS 2 this past weekend, and they've created a video out of it. So from Ubuntu 22, so the Ubuntu and the ROS typically they go hand in hand. So ROS Melodic, the version before Noetic, worked with Ubuntu 18.04. ROS Noetic works with 20.04, and the next ROS works with the next version of Ubuntu. That's how it goes. They go hand in hand. They wait, and if Ubuntu upgrades, you get a new ROS version. Okay, now, so what we're going to do in this short lecture is we're going to learn the basics, understand the basics of ROS. The architecture of ROS. Why is it so useful? Which is essentially the key characteristics of ROS that makes it so useful. And then we're also going to talk about your programming environment, right? The programming language rather. So ROS is ROS, but you can work in ROS using Python, C++, Java, MATLAB. Actually a mix of all of those. It's possible to do one part in Python, one part in MATLAB. It gets very complicated. So we're going to use MATLAB purely because it's a very easy language to develop software in. Much faster than C++. Okay. So we'll talk about that. And then there'll be a demo of a ROS operation in terms of a very simple simulation. So this is from my students, and you'll see what they did with ROS. And that example actually captures just about every aspect of ROS. That's the beauty of that application I'm going to show you. It's a captured application. I've got a screenshot, a video of what is going on. And each one of those pieces we learn tomorrow. For instance, we use a simulator, robot simulator called Gazebo. So Gazebo is the GAZEBO. It's the commonest simulator that is used with ROS. So ROS and Gazebo used to be like cousins. They were the same open source family. But then ROS asked Gazebo to get lost. Well, no, not quite like that. You see, anytime you have this relationship, like if you have your brothers and sisters working in your company, it doesn't make for a very efficient system because you will not be honest with your family. So Gazebo split off as a separate open source movement. So that means that Gazebo also has to look for other ROS-like software to interface with. ROS is not the only game in town. ROS is the most popular game in town, but there are other people doing similar stuff. So the backside of that is ROS now operates not just with Gazebo, but with many other robot simulation environments. So at some point, if I remember today, if not tomorrow, there is a simulator called Carla, C-A-R-L-A. You should go to their web page and take a look at it. It will completely floor you. You have cars running down simulations of streets with wet roads. So they're able to do that. It's a much more sophisticated simulator compared to Gazebo. And you know why? It's because you have to pay to use Carla. So auto companies sometimes use Carla. There are several competing for the auto company's attention, and all those are paid for. So therefore you get much better features. The scene looks great. You can change the friction under the floor because when a car drives on the streets under different conditions, ice, snow, very hard conditions, then the operation of the car is different, right? So if you're designing a real world product, then you have to be aware of all of those. What if you have different friction coefficients under the four tires? Well, we get that all the time in North America in the winter. So how do you design a system that will maintain stability when you have the four tires on surfaces with different friction coefficients? Only a simulator will help you solve those problems. Now, of course, you can go out, but is it possible to find a test track with different friction under the four tires? Now, how do you create that, right? So a simulator That's the beauty of a simulator. It helps you create all these conditions at very little cost. Of course, the simulation is not the same as the real world. So eventually you got to go test. But by using a simulator, you eliminate most of the problems, you find solutions for them, and then you can go out and test. So you can't avoid real world testing, but the simulation helps you save money because you eliminate a lot of possibilities. So it's an open source software platform that basically works only for robotics. It works for the other robots also. The arm robots, it works for that also. So, you are in medical robotics, so the first thing that comes to mind is surgical robots. Now, you will be able to find robots with arms, multiple degrees of freedom, wrists and so on, that you can download and play with. You just need to find them. The image we gave you, right, is geared for the Turtlebot 3. So you might not find those packages in the package we gave you, but you can add them on. And then you can actually move an arm, pick up an object, and do all kinds of fancy things. So it was developed roughly 17 years ago by a small group of people who are still around. They've just moved to the ROS platform now, because they started with Player Stage. Player Stage is what we started with back at my university. Player Stage is now abandoned. You can find it on the internet and use it, but you have to fix all the bugs because it's like a house that has been abandoned because all those people moved on to ROS. So ROS is called a meta operating system. So this morning we talked about operating systems. The real one, which is Mac OS, and then the virtual one, right? Which is Ubuntu. In your case, Windows and Ubuntu, right? So we talked about two operating systems, but only one is a true operating system because it is controlling the machine. The other one is fake. But at least they are operating systems. ROS is not an operating system. So why are they calling it meta operating system? They're saying it's like an operating system. I'll tell you why. If you want to work in robots, right, you often need to do a whole bunch of standard things. Like what? Like for instance, somebody's already written a computer vision program that looks at an image and detects lane lines. And that software is available to you, right? Now, do you want to write it again yourself in your robot application, or would you rather plug into that application? So ROS gives you that ability to take advantage of all that software that's out there because they bring it in the form of packages. So literally you are snapping parts together. You're not building the part, but you're snapping parts together to create your application. It used to be in the old days, like 20 years ago, a PhD student would be writing his own vision algorithms if it was part of his thesis. You can't get a thesis by doing that anymore. It's all done. That work is already done. So essentially, now we are doing higher level applications. We are picking these pieces together and making them work together and maybe value adding to some of them. You can't get a PhD just by writing a lane recognition algorithm because it's already done, right? Face recognition. I believe you'll find packages for face recognition in ROS so that you can use the camera on the robot to identify somebody on the move. So that's why they call it an operating system, a meta operating system. Because what is the job of an operating system? When you want to print to a printer, do you go and look up the hardware of the printer? Well, that was the original purpose of an operating system, to avoid you having to figure out how the printer works, right? How the CD drive works. Well, ROS is doing the same thing for robotics. It's giving you all the common functionalities of robots. So for instance, you put a new LiDAR on your robot, right? A fancy new LiDAR, with much better resolution. In the old days, you would be trying to write a driver for it. A driver is typically software that drives a hardware unit. You need that, otherwise you'll have to go in and apply voltages and currents. So the driver says, okay, you go back, you don't need to see what's inside. You just do this and this and you're fine. You'll get the LiDAR data. So we don't print to a printer by figuring out how a printer works deep down, right? So the print command basically is like a mini operating system. It gives you all the functionality of common interface devices. So ROS does the same. So ROS has a driver for many of the common robots, like the Turtlebot 3. There are many, many others. Now, obviously the auto companies have drivers for their cars, but that is proprietary because they've invested in their employees a lot of money in building that. So that, you won't have access to. But ROS gives you all the common stuff. So what happens if you have a new LiDAR and they haven't made a driver available? Then, if it's really urgent, you've got to jump in and write it yourself. There's no other alternative. So that needs a little bit of skill, how to write a driver. If you ask me to do one now, I will not be able to do it, but it's possible to figure it out. Or you can look at an older driver and by example, make the changes. Is that clear? So because it's an open source community and you can't pick up the phone and shout at them, there'll always be a delay. That's why at my university we are slow moving to the new Ubuntu and new ROS, because if we move and the drivers are not available we've got many, many robots sitting around. All of them will be useless. So we always wait till the new Ubuntu and ROS is accompanied with the drivers. Only then we move. So I told you about the LTS, right? LTS is long-term support. So when the LTS is expired, it's time to move really, because at that point they are not applying security patches or anything. Because it's not that they don't care. The same group of people are working on something newer. So at that point, it's good for you to move, because you won't have support for the old operating system, or even the old ROS. Even ROS has an expiry date. So I don't know when ROS Noetic is expiring. The 4 years, 5 years I think have gone by. So it's close to expiry. So we'll all be forced to move to ROS 2. So Ubuntu 20.04 is the last one that gives you a bridge between ROS 2 and ROS 1. After that, you have to move to ROS 2, or you have to create your own bridge, which is not an easy task, right? Because we don't specialize in that kind of thing. Okay. So what is the auto industry using? Nobody knows. I've gone to trade shows, self-driving car, exhibitions, and when they open the screen, it looks exactly like ROS. It's the same Ubuntu look, but it's proprietary because they've taken ROS and Ubuntu, which is open source, added a lot of stuff to it, right, and locked it down, and now it's a secret. If you get hold of that, they'll probably take you to court. So it's their own now because they've added so much value to it. But it looks very much like ROS and Ubuntu. So we don't know what the auto industry uses. They use something like ROS. Okay, so this is the heart of the discussion here. A brief understanding of the architecture of ROS. So, I'm not sure about ROS 2, but ROS 1 requires a single master. So there has to be a master, like a boss. So there has to be a ROS master. That's what this yellow block indicates. So if ROS core is not running, nothing will run in ROS. If there is already a ROS core running and you try to run it again, it will say there's a master already running. So under the ROS master, you can run many nodes. Now on the next slide, you see an example of what a node is. So Unix is nice in the sense that it allows multitasking. So different things can go on at the same time. So you can run 5 nodes, 10 nodes, 15 nodes in parallel. Now why would you want to do that? Because we are typically trained to think in terms of a single program, right? Maybe long program, maybe even longer, but a long program that does everything. That's not the way that real-time software works. Anytime you're working with a robot or a self-driving car, time is of the essence. You can't take 4 hours to process something. Now, when can you take 4 hours to process something? Let's say you're processing a company's payroll. Nothing is immediate, right? Now, of course, you can't give the results of the payroll after 1 month. But certainly you can let it run all night, right? There is no immediacy. But when you're driving your car and maybe you have a couple of your kids in the back seat who are banging on the back of your head, and the traffic is congested and people are crossing the street, that's an example of a real-time system. So you have all this information coming at you, right? And as a human being, you're processing them simultaneously without even knowing it, because nobody tells us, parallel process when you grow up, right? We just do it. So we ignore those sensory inputs that are less important, right? And focus on the ones that are most important. And every once in a while, when nothing is urgent, we even look at our phones, and some even text while driving at 100 miles per hour. So that means the immediacy is over, so you can, pay attention to this less important task, which is, maybe responding to your wife's text message or husband's text message. Got it? So a real-time operating system has to be fully conscious of what is going on. There is always a priority order of tasks. So the only way you can accomplish that kind of a performance is to have multitasking. So these nodes allow multitasking. And on the next slide, you'll see what an example is. What are good examples of multitasking and nodes? Now, we, at some point, either today or tomorrow, we're going to fire up a Turtlebot 3 robot in Gazebo. The window that you use to launch Gazebo, right? It will not close. It will still be open. That terminal window will still be open. So don't worry about it. Don't say what's going on here, let me kill it. If you kill it, you kill Gazebo. That process is going on permanently till you decide to shut down for the day. Is that clear? So what do you do if you need to enter another terminal command? No, you go and open another terminal window. Is that clear? So there is a program known as teleop, which you can use to move the robot around. For that, you open a separate window, right? And then when you launch it, it will not close, because it's thinking that any time now you might want to, hit a few keys and move the robot around. Don't touch it, leave it open. So when you work in ROS, you realize that sometimes you can have 5, 6, 7, 8, 10, 15 of those windows open. They're all processes running in parallel. And they're meant to be alive. Don't kill it, because when you kill it, you kill the process. How do you get out of one of those processes? Control C. So you interrupt by hitting a Control C. When you're done, you hit a Control C. Even if something is jammed, you hit a Control C to get out of it. If you want to launch Gazebo again because it froze in the middle, hit a Control C and run it again. The topics and the concept of publishing and subscribing go together. So there are two modes of communication between nodes. Okay? Always the master is there. It's in the background looking at everything. See, all of these nodes need to register with the master. They can't be outside the purview of the master. The master is the boss. Nothing happens without the master. So all these nodes, they register themselves. When you launch it, it gets registered to the master. The master knows what ROS node 1 is in terms of how do you communicate it. And then they send messages to each other. Messages and messages, right? They only register once. Notice, the messages don't need to go through the master. You only need to register with the master. Then the messages can go directly from node to node, or in a slightly different way, you can publish them to a topic. It'll get better as you see example on the next slide. So this is the architecture of ROS. There are two forms of communication. One is publish and subscribe, and the other is services, through services. So topics versus services. So topics means topics, you publish on a topic, publish and subscribe, publish to a topic and subscribe from a topic. That's one form of communication. And then there's another form of communication known as services. And the next few slides will explain the difference between the two. So we can come back here later if you want to see it. If you missed something on this particular slide. Now the form of the communication is the standard TCP/IP protocol. So TCP/IP protocol is used for the communication. So typically in robotics, you can have multiple computers. And not only that, these computers can be all over the world. You can be running an image processing or vision algorithm on a super fast computer in Tokyo. Of course, they have to give you permission, right, for access. But if they give it to you, you can run this very dense, complicated AI-based algorithm on a computer in Tokyo. So you can have computers distributed all over the world. In fact, right now there are companies in Europe, if you don't have a fancy robot, but you're very good at developing software, you can buy time on their robot setups. They have rooms with robot setup. And then you can download the code. So you buy an hour, right? And you have a camera image, you can get a data flow back to you want to collect data always when you're running something, because you don't want to just say, oh, it did not work, let me go and fix the bugs. How would you fix the bugs if you don't know what exactly failed? So they'll give you a data feed, a camera feed, you can look at it and you can use the 1 hour. Of course, after the 1 hour, they're going to cut you off because some other customer is waiting for the next hour, right? So you have to have an account and funding, and you can run your code on sophisticated robots. This company maintains them. If something goes wrong, maybe the battery on the robot discharges, there are people there who will, and maybe they won't charge you for that time. So they'll recharge or swap the battery, and you can run again. Maybe the robot falls over. They'll come and correct it. So computers can be distributed all over the world. IP address is a form of communication. Image processing could be running in Tokyo. Some other sophisticated face recognition algorithm could be running in Canada. This architecture supports that. You can distribute your tasks. So the concept of the node is important. Here, these nodes are running on the computer on the robot. So typically it's the computer on the robot, but there's also a laptop where you're sitting down with a cool drink under a tent. Because robot, obviously, if it's a big robot, you're going to run it outside. But in the laptop, you're just looking at the data. Robot is about 50 yards away. You don't want to go to the sun. So this laptop is, I'll get to this image display node. We'll start with the camera. So somehow the line got missed. But the camera is publishing. Oh, I'm sorry. The camera is giving data to the camera node. So this line is missing here. It's there in the original, but I think the resolution here is throwing it out. So is that clear? The camera is sending its image data to the camera node. Now, most camera nodes now do some simple processing. It's built into the embedded hardware. So maybe the camera node is not just collecting the image, but it's doing some simple processing. But this is simple. This is much more complicated. Image processing node could be extracting the lane lines. Is that clear? Now, there isn't just one method of extracting lane lines. When you have a self-driving car, you have to be sure it doesn't fail, right? So how do human beings perform well in tough tasks like driving in Chennai? Because we have something known as redundancy. We have much more information than we need. If we just count on one piece of information or one source of information, things can go horribly wrong. But we use multiple inputs, right? We can't explain it even. We don't even think of it as redundancy. We just do it, right? So you may have other lane recognition algorithms completely independent, right? So there could be algorithms that is just using the structure of lane lines. See, lane lines typically are parallel and they have a certain distance apart. So somebody could just say, I'm looking for two lines that are so many feet apart, right? So there could be multiple algorithms. You could be running them on separate nodes. And then you will collect all their decisions. And so if the decisions agree, or most of them agree, you're confident that this is the lane line, right? So that's the beauty of having these nodes. You can have different computers or even different nodes within a computer running these different algorithms. So that's what is going on here. They show only one node, but you can have multiple image processing nodes doing the same end result. Like, I want lane lines, not the same method. What's the point of having multiple nodes do exactly the same method? You want to use different methods to arrive at the same result. So you can have several of them. So the camera node, having done its basic processing, it publishes the message, and every message has a message structure, right? Because we're talking about numbers. What comes from the camera won't have the same structure as what comes from the LiDAR, right? So it has a message structure. This is image data. So this image data message. So camera is publishing to So think of this. So this is topics, right? So think of it as you have a result, you go and put it on the bulletin board. When you put it on the bulletin board, do you know that anybody will read it? No. If somebody is interested, they'll read it, right? You can put anything you want on the bulletin board, but you can't force anybody to read it, right? So you just publish. So the publisher can publish without even having one subscriber. So typically it won't make sense to do that, but you can go on publishing and nobody even looks at it, right? A subscriber, if he's interested, he'll go to that, he'll subscribe to that topic because it's the topic that's being published on. So the subscriber will subscribe to that topic. So you got it? Tomorrow you'll come by the bulletin board and say, oh yeah, I find this interesting. And you take that information. And the information is constantly refreshed. New image process data, new LiDAR process data. You get it? So it is asynchronous. It is not synchronous. You keep on putting new information and whoever's interested in it keeps on grabbing it. It's asynchronous and that is good in many situations. You know why? Because somebody says, hey, new data, right? It's too much for you to handle because you've got other things to do. When you're interested, you get the most recent, only the most recent matters, right? If you miss 2 or 3 frames of image data, does it matter? Because no, that's in the past. The car has already moved past that spot, right? So the publisher publishes at a certain rate. And you get it, you can do a check and say, is this fresh? Meaning, is this new data from the previous frame? They have a flag there. And then if it is fresh, you can grab it. But all the missed frames don't mean anything to you because that's in the past, it's over. So you don't have to process every piece of data. Whenever you're interested, you go and get the latest piece of data and process it. So that's the model of this publish subscribe. I publish when I have a new frame of data, you take it whenever you need a new piece of data. It's great if they take every frame of data, but that's not the way humans operate in the real world. There are lots of things we ignore because we just can't process everything going on around us, right? So that's the model of this topics. So notice the camera node is publishing to this and the image processing node is subscribing from it, right? You also want to display the image at a remote location in a laptop, so that's also subscribing. Do you think it makes sense for the image display node to publish here? I don't think so. Because it's displaying it, right? The word display says it's passive. It's just looking for something from someone else. So obviously this is only a subscriber. It's not a publisher. And this could be anywhere in the world. You could have the laptop miles away from the actual robot. I told you, there are companies in Europe that sell time on robots. Think about how complicated this becomes. You could have 5 cameras, this way, upwards if it makes sense, and so on. So all of that is going on at a high pace, multiple nodes running. And you take it when you think that you have the time to process it. Now, of course, if you don't process things fast enough, you're going to crash, right? But that's for you to figure out. The publisher doesn't care. It's for you to sample at the appropriate pace. Knowing that you don't have to process every frame, because you don't really have to process every frame. There's so much redundancy that you process fast enough to survive. That's topics. I'll briefly touch on services. So, anybody notice the difference here? Same ROS master, camera node, image processing node. Notice, let's go back here. Everybody's publishing here. Here, you have direct, request, and reply. So this is a synchronous form of communication. That was asynchronous. Put it on the bulletin board. If you want it, take it, but I don't need to know about it. Here, you make a request. At this time, you're ready, right? You want a new image. You say, give me the new image, like a tap on the shoulder. Hey, give me a new image. And you give it to him or her. Got it? So the time can be controlled. In certain applications, the timing is very important. You want the image now. You don't want to go look on the bulletin board and say, what is the last frame? You want the image now, and you get it now. So it's a direct one-on-one. Most of the time you'll not use services. I've never used a service in my ROS work. Topics you use all the time. Not that it's unimportant, but the application has to rise to a certain level for you to need services. So the beauty, just to summarize, it permits task distribution. If you did not have this node, topics, right, and services feature, you could not distribute it. And in robotics, you have a lot of different things you're doing. You're trying to read the rate at which the tires are spinning. You're trying to read the speed of the vehicle. So there are many pieces of information you want, and therefore task distribution is what you want. So different parts of the overall software suite could be run on different computers. Even embedded processors. Embedded processors are dedicated electronics, which are high speed. So some nodes can run on embedded processors. Your car has many embedded processors inside the engine. So it enables hardware and software abstraction. So for those of you who don't understand this word, so abstraction is where you don't have to know the details. Like it's kind of summarized for you, and you're told that here's the inputs, these are the outputs you get. Don't ask about what's inside because it's none of your business. So abstraction is stepping back from the details of the box or whatever it is, or the algorithm. If you want to recognize faces, you don't have to know every line of code. You just want to present a face and get a result, right? So it tells you how to do that. Face recognition, it tells you here stand here, and here's the result. So you don't need to know how each line of code works. So that's what abstraction is. It pushes you away and says, you don't have to come any closer, you don't need to know any more details than this. Device drivers, I already talked to you about this. Device drivers are those pieces of software that communicate with hardware. Image processing algorithms, also known as computer vision. Path planning. So there are path planning. I'll show you in MATLAB as we go further. There are path planning algorithms in MATLAB. Navigation algorithms. So you don't have to write those anymore. Unless you're developing something even better. If you're developing something even better, then obviously MATLAB won't have it, and you're going to write it yourself. So if that's your area, if that's your PhD work, you'll do it on your own. Because how can you do a PhD on something that's already done? So it'll be something that you have to write. So you can focus on higher level tasks. If available packages don't address specific needs, then you have to write it yourself. Now remember, it is the open source community. So you won't find the latest and greatest because they are not there to serve you. They're just doing it in their spare time. So there's always a delay. If you are impatient, you have to jump in and write ROS packages on your own. And some of our students, we teach them how to do that. It's not difficult. There are web-based descriptions of how to do it. But as always, anything new is slow. As you're learning, things are slow, and then it gets better and better, and you get faster. Okay, let's just briefly talk about languages. So we're going to use MATLAB. MATLAB is sitting on the host computer. The host computer is your Windows computer. For me, it's the Mac. You also have a guest operating system, right? Your guest operating system is running Ubuntu. So therefore, you're dealing between two computers. No, you're saying I have only one computer. No, the virtual OS, Ubuntu, is a separate computer. For all practical purposes, from the software point of view, it's a separate computer. So you have to communicate using TCP/IP. If MATLAB were to be downloaded inside Ubuntu, and that can be done, then you only have one computer because MATLAB and everything is inside your virtual computer. Now that's not the way your computer is set up, neither is mine. Because I need MATLAB on the host side, right? So if I install MATLAB again, MATLAB chews up a lot of memory. So if I install MATLAB on Ubuntu, I can, but I'm kind of filling up my disk when I already have the software. So I prefer to keep it as two separate computers. So the beauty of MATLAB is, it's the fastest development language, one of the fastest. Because of its libraries, it has many powerful libraries. And the other thing that makes it fast is, MATLAB is not a compiled language. MATLAB is a scripting language, it's an interactive language. So when you run a program, right, you can put a pause in the middle of the program. And then you can go and look at the variables. And if the variables are not what you think they should be for your test data, you can say, okay, I made a mistake here. But I'll get to that later. I'll fix that later. But right now I'm going to change this intermediate result to the correct intermediate result. Let's see how the rest of the program runs. You can't do that in C or C++. C is a compiled language, meaning that once it's compiled, you don't have any access to it anymore. Of course, you can put intermediate printouts and run it again. But MATLAB, I can dynamically change things and figure out how it runs. I can take 10 lines of code, bring it down to the workspace and say, run just this. You can't do that in C, C++. It needs the whole thing. In MATLAB, I can just run by sections. Run the first 10 lines, then the next 10 lines, and so on. So because of that, debugging is much easier in MATLAB. So you can develop an application in much shorter time than C, C++. Of course, C, C++ does not cost you anything, it's open source. Python does not cost anything. And by the way, Python is MATLAB's cousin. It's the open source cousin of MATLAB. It is a scripting language also. It has big, powerful libraries. So why are people using MATLAB? Well, you know the problem with the open source community, right? You can't pick up the phone and shout at anybody. MATLAB, you can pick up the phone if you have paid their license fee. If you've got a hacked copy, then of course they're going to shout back. I know people in China, a lot of people have MATLAB copies and they don't have a license. I don't know how they did it, I did not ask. So, MATLAB, you can get your problem solved by filing a ticket. Python, you're on your own. You can ask the user community, they'll help you. But you may not immediately solve your problem. But Python is free. So take your pick. If you like help and support, then go with MATLAB and pay thousands of dollars. So I told you this, motion control, scene, sensor perception, all these packages are available. Mapping, smart planning, navigation, all of these are available in ROS. Now, Gazebo simulator is the commonest simulator because it started off by being in bed with ROS, then they kicked them out. But now most people stick with Gazebo. Carla, we'll check it out. Carla is much more sensational in terms of what it looks like, the looks. RWiz is built into ROS. We'll see what RWiz is capable of doing. We'll also look at what Gazebo is capable of doing tomorrow in greater detail. Also, there's a feature known as ROS bag that's built into ROS. So whenever you run a system, any system, an engineering system, you like to keep a log of, okay, something's going to go wrong initially. You will never get the algorithm running. So you like to keep a data log of everything, all the variables you think are important, right? Versus time. Maybe you have a 5-minute run, somewhere in the middle it hit an obstacle and you're saying, I have code there that avoids obstacles. How did this happen, right? There's no point in running it again, right? Many of my students say, okay, let's run the algorithm again, maybe you'll get lucky. Even if you get lucky, you still haven't solved the problem that it did hit an obstacle on the previous run. So you can log the data in a feature known as ROS bag. You can bag the data and then you can go back and look at it in the lab. You can run it on a simulator now. You collected ROS bag on the actual data or on a simulator. You can rerun it. You can recreate the exact conditions. You can slow it down. You can say, okay, slow down. This is the obstacle it hit. Let's see what the data is showing. And you'll be able to debug the problem. So that's what ROS bag is. It comes with ROS. There's also something called RQT graph, which you'll see shortly in the example I'm going to provide. It's a graphical debugging tool. So here it is. So I told you about multiple nodes, right? You can't read this, but maybe you can on the version you have there. But what it's essentially showing is, it's showing you all the nodes that are open in your application. And here there are quite a few nodes. This is not connected with this. I just got this from the internet. This RQT graph, when you run it, it will pull up something like this. It is a node map. Sometimes you're wondering, right? Why is this not taking my data? It's because you haven't set up the subscription. You know what I'm saying? Because there are so many things going on. You're publishing to the bulletin board, but nobody's looking at it. What's going on? And then if you look here, you'll say, hey, that's not subscribing from the bulletin board. I forgot that. So that is the beauty of this graphical display of nodes. Now, of course, if you have 253 nodes, it's not going to be easy to show the printout on paper, but then you'll have to find a way of, moving it on the graphical screen and figuring out, what is missing, what is not connected, what camera is connected to the wrong node for processing. All of that you can figure out by this RQT graph. So we're not going to use RQT graph. I just wanted to show you that all these tools are available. Now, so watch this. We may have to run it a couple of times, so that you get your bearings. You figure out what is being shown. So don't panic. We'll run it and then we'll run it again. Maybe I'll give you a little bit of a setup. So the students created, so we do a lot of competitions where a robot has to navigate between lane lines, and the lane lines are drawn with paint on grass. So it's not very bright. And during the competition, if they cut the grass, then if there's very little paint to start with, it might completely remove the paint in patches. So we try to create a simulation so that, I told you, right, it's much easier debugging in the simulation environment than with the real robot. And so here is what we did. We have these lane lines. The robot is somewhere down here, our robot, and then you have a few obstacles, so the robot has to go around and get to this target position. Now here you have a snapshot of RViz, which you haven't seen yet. So it's something that enables you to look at the sensor data coming from the robot. So that's what RViz is. You'll see more of it tomorrow. And so let's just run it. I want you to correlate between what's happening here, here, and here. So one is a frontal view. In the middle, in the panel, you see a frontal view. There's mapping going on in the right side. And this is very bad navigation because the robot is swinging around as if it is drunk. Okay, let's run it. Oh, it's not finished. I'm sorry, the contrast is a little bit poor, but you get the idea. So that's the end. Let me run it again. So here you're seeing what is known as a bird's eye view. This is the point of view of the robot, right? On the right, mapping is going on of the scene. Because if you're going to go through the same obstacle course, then a map is going to help the next time around, right? The first time you don't have a map. The second time a map is going to help. Remember I showed you in my talk how the map helps you make better decisions? And here you have the RViz, which you'll find out what it is tomorrow, displaying some sensor input. Okay, let's run it again. So you see how badly the navigation algorithm was at that time, because it overreacts. This is fine, but then somewhere here it's going to face the lane line because it's going to turn too much. Right there, see? That's too much. So that helps you correct navigation algorithms. Too much of a turn away from the obstacle. And the map is building on the right. Now you might say that was unnecessary. You could see the obstacle, why is it going back into that corner and then going out? So you can fine tune the algorithm by looking at its performance. That's a little bit too much too, Now if you drive like that, you know what I'm saying, right? If you're designing a self-driving car, the passenger is going to, vomit. Go like this for simple situations. So you agree that the simulator helps you solve many of the design issues without having to do it on an actual vehicle. So you can figure out these problems and solve them. So the platform itself was a Segway. If you've seen on YouTube, a person standing on it and driving it around on the sidewalk, it's called the Segway, S-E-G-W-A-Y. So we're going to explore on our own. But the first thing, well, not the first thing, but I want to point out this because the theory is coming later. And tomorrow, you're going to be using the result of the theory without knowing where it came from. So when you have a differentially steered robot, does everybody know what a differentially steered robot is? So basically it has two drive wheels. The Okay? Independent motors. No steering wheel. So it's not like the car. So it's a very common robot architecture for up to about 125 kg of weight. So 125 kg is quite a bit, it's more than 250 pounds. So it's used in many, many applications. So 2 drive wheels, separate motors, no steering wheel. So how is it going to steer? So if you spin the right wheel more than the left, right? It will turn this way. Got it? If I spin the left wheel more than the right, left wheel more meaning faster, it's going to turn this way. If I spin both wheels at the same speed, it will go straight, right? If I spin both wheels at the same speed backwards, it's going to go backward. What if I want to go backward and turn this way? So I spin this wheel faster backwards than this one, right? So it's a highly mobile vehicle, as you'll see. Turtlebot 3 is a differentially steered robot. Now, the theory will show in a day or two that if you keep the forward velocity constant, V, constant, and the turn rate, so the forward velocity is in meters per second, right? Everybody understands that. The turn rate is radians per second. So these are the 2 control inputs for the robot, V and omega. So if you keep V fixed and omega fixed, then it will be on a circle of radius V divided by omega. So that theory you can accept now. We're going to prove it in a couple of days. V by omega in meters. So V is in meters per second, omega is in radians per second. So R will be in meters. That is the radius of the circle. So if you don't change V and omega, it will be on that circle forever. But of course, who's interested in a robot that goes in a circle forever, right? You want to make it do fancy paths. Well, that means you're going to change the radius frequently. So you're going to change the radius from moment to moment to moment to moment. You can do that by changing V, or changing omega, or by changing both of them, right? So there are many possibilities. So you can do a piece of a circle, another piece of a circle. So you can do tiny circles, right? Do you get that? By changing V and omega in some intelligent way, I can create tiny circles. So one circle ends in another circle, and then another circle. So I can create fancy paths. You'll see that it's possible to do that. So that's how a differentially steered vehicle operates. V and omega sets up an instantaneous circle. Because we say instantaneous because most of the time we're not going to let that circle go for 2 hours. It's going to be for a few 100 milliseconds at a time. And so you're going to get very fancy paths. So this is the last slide. I just want to give you an overview of the software, the main piece of the software, which is ROS, of course. Ubuntu is just facilitating ROS. So that you understand the place of different things, right? It's never a good idea to just jump in and not know what the other pieces are that are responsible for what you're doing. Now, it's going to be slow, so don't be impatient. It was slow for me, it's going to be slow for everybody. So when you get stuck, the first thing is, you have to ask yourself, did I follow instructions? And then if you followed instructions, you have to know precisely what you did and what happened. And then we can solve the problem. So none of these problems are insolvable. They're all, can be solved. Some may take more than others. Okay, so now let's get back to Ubuntu and solve that problem of why ROS code is not running.